Okay. Welcome everyone to this afternoon session. So it's my pleasure to introduce our next semi-plenary talk. Laura Mancinska from the University of Copenhagen will speak on certification of quantum devices via operator-algebraic techniques.
Thank you. So it's my pleasure to talk to you today. Thanks to the organizers for giving me this opportunity. And I want to tell you about how can we verify proper functioning of quantum devices, and in particular, how operator algebraic techniques can be useful for this task. All right. So I'm going to start with intuitively explaining this concept of certification of quantum devices, what's the problem, and then later on I'm going to go into more technical details and tell you about the math behind all this, right? So the beginning part is going to be kind of just a big picture. All right. So we have this fundamental problem that given a quantum device, how do we know that it's doing what it's supposed to be doing, right? So maybe you go somewhere, you buy this huge machine that's probably not so cheap, and it comes together with certain claims about what it's supposed to be doing. The problem with quantum devices is often that we cannot directly observe what they're doing, unlike kind of conventional computing devices, right? But at the same time, kind of the security, say maybe you're using this quantum device to run some cryptographic protocol, and then the security of your cryptographic protocol could crucially depend on proper functioning of this quantum component. All right. So given a device, how do we know that it's doing what it's supposed to be doing? In particular, I'm going to be talking about verification of two elementary quantum functionalities. Okay, and you can actually view any quantum protocol as being built up from these elementary building blocks. Okay. So the first one is production of quantum states. So you can imagine that this is a box where you press a button, and then out should come a specific quantum state. Let's say a photon polarized in some specific way. Okay, but mathematically, this would be described by some unit vector in a complex space c to the d for some dimension d. All right. And the second elementary functionality is that of performing quantum measurement. Okay, so here you have a box where you put in a quantum state, and then out comes your measurement outcome. Let's say in the simplest case, it would just be a binary outcome, so just a label 0 or label 1. And then mathematically, we specify such a two-outcome measurement, or we specify measurement using sets of positive operators that add up to identity. Okay, so for every outcome, you have one positive operator. If you just have two outcomes, and I will only have two operators, so this E0 and E1, and I want that they add up to identity. All right. So, and I'm going to be interested in certification in the scenario where you have these quantum devices, but you don't have any devices that you trust. Okay, so you have maybe a bunch of these boxes, some produce these quantum states, some perform these quantum measurements. You don't know that any one of them functions properly, and you would somehow like to certify this. Okay, and verification in this regime, the term used for it is self-testing. Okay, it's just historically this term is being used, so I'm going to use it as well. So if it's confusing to you, then in your head you can replace, whenever I say self-testing, just think verification with minimal assumptions. All right. And if you think about this a moment, then it is perhaps curious that this is at all possible to do, right? So we have these devices, and we don't know that any one of them functions properly, and we want to somehow gain confidence that they indeed do function properly. So this is like you were given a scale that's potentially faulty, and you were given a block of weight, and someone said, oh, this block should weigh 1 kilogram, but you don't know that any of these claims is true. So how do you use these these two things you have to say that these two claims are correct, right? If you knew that the block of really weighs 1 kilogram, you could just place it on the scale and check whether the scale says 1 kilogram, right? But the problem is that you don't know that any of these two claims are true. So the same would hold here. If we had trusted quantum state preparation boxes, we could test our quantum measurements and vice versa. And the difficulty here is that we don't have either of those. So what do we do? The kind of intuitive idea is to do something similar, like if you had several witnesses and you suspected that they are not telling the truth. So what you would do is you would put them in separate rooms and interrogate them separately. So this is what we're going to do then, what we're going to do as well. So we're going to take several of these measurement boxes, and we're going to give some of them to Alice and some of them to Bob. And then we're going to enforce in some way no communication between Alice and Bob. And we're going to ask Alice and Bob some questions, X and Y, and then observe what answers they provide. Okay, and we're going to do this a bunch of times and collect statistics to estimate this joint conditional probability distribution here. So what is the probability that given questions X and Y, Alice and Bob respond with A and answers A and B respectively? Okay, and I'm going to refer to this this collection of probability distributions as correlation. All right. Now, in such a scenario, a generic verification or self-testing statement would look as follows. This is an informal statement. I'll show you the formal statement later on. Okay, so it would say that if you observe that Alice and Bob produce this correlation P, then there's essentially just one way for them to do this. And this is by sharing some specific quantum state psi, remember some unit vector, right, mathematically, and by performing some specific quantum measurements, okay, so these AXAs and BYBs. So these are these sets of positive operators that I'm indexing using questions and answers. All right. Okay, you might not only test these devices from this full correlation P, but just from some linear function on P. Okay, and this can be phrased as some sort of game, right? So here the questions and answers are just 0 and 1. And suppose that what you want Alice and Bob to do is to output A and B so that the XOR of A and B is equal to the product of X and Y. Okay, and if you see that Alice and Bob manage to output A and B that satisfy this boxed condition with some with a sufficiently high probability, then you can be sure that they must have shared this specific quantum state and performed some specific quantum measurements. Okay, so this game is actually known as CHSH game, and it's very often used in quantum information for various tasks. Okay, but in practice, we're actually interested not only that in order to produce a specific correlation or to win a specific game, if you're doing this exactly optimally, then you can guarantee what the state and measurements are, but we are interested in robust versions of this statement. So what do I mean? We want some kind of noise resistance. So we want that if Alice and Bob, say, play this, succeed at this CHSH game near optimally, close to this optimal probability, then they must share a state that is close to this optimal state and perform measurements that are close to these reference ones. Okay, and the reason why we care about robust versions of these verification statements is that whenever you try to build some devices in the real world, there will inevitably be some degree of noise, right? So you will never be able to observe kind of this exact correlation or this exact highest possible success probability. Okay, that is one reason. And another reason is that the only way for us to access this correlation P or see what is the probability that this orange condition is satisfied is by performing this experiment many, many times, right? So we will just have some error from statistics, right? From finite statistics. Okay. So Now, let me try to move towards showing you what goes behind this word essentially. Okay. So a quantum strategy in a scenario like this is specified by three things. One is this quantum state that Alice and Bob are sharing. So it's some unit vector in a tensor product space, some C to the D tensor C to the D prime. Okay. And then we also have these sets of measurements, one for Alice and one for Bob. Right? So for every input X, Alice has a measurement, and that will correspond to positive operators that add up to identity. Okay. This here I'm ranging over X and A, and here we're ranging over Y and B. Okay. Given this triple, the strategy, that if Alice and Bob act according to it, right? So when they receive these questions X and Y, they perform the measurement corresponding to X and Y respectively on this shared state. Okay, then the probability that Alice and Bob will get outcomes A and B, given that they perform these measurements X and Y, is given by this sort of inner product. Okay, so you take this shared state, you sandwich it around this operator AXA tensor BYB. Now, what we could ask is, what sort of transformations on this S tilde we cannot observe at the level of this correlation, right? How could I change this vector and these sets of positive operators so that the correlation that I obtain remains unchanged? Okay, so there are two kind of suggestive ways that I can do this. One is I could perform a local change of basis. Okay, so I apply some local isometry, so some isometry U, tensor isometry V. Remember, this was a state that lived in a tensor product space onto my state, and then I kind of undo this isometry on my operators. Okay, so when I plug these this new state and new operators in here, then I'm simply gonna get things like U star U, which is identity for an isometry, or V star V. Okay. So this strategy has the same correlation as this S tilde. So if I only see this correlation P, there's no way for me to distinguish between this strategy and the strategy S tilde. All right. So another way we can modify our strategy is by giving Alice and Bob yet another state on which they are doing nothing. Okay. So instead of the shared state just being psi tilde, we also give Alice and Bob some complex unit vector phi in some other tensor product space, right? Where one part belongs to Alice, one part belongs to Bob. And then they're doing these measurements, they're doing nothing on this additional state. Again, because this phi is a unit vector, if you evaluate this expression for this updated strategy, then you will see that it gives you precisely the same probabilities as the strategy S tilde. Okay, so now keeping these two things in mind, we're now ready to move on to formal definition of the self-testing or verification. So first, I'm going to introduce this notion of local dilation. Okay, so let's consider two quantum strategies, S tilde and S. And remember, this quantum strategy was a triple, right? This quantum state, and then measurements for Alice, measurements for Bob. And the same for S. I have two strategies. Then I'm going to say that S tilde is a local dilation of S, and I'm going to denote it using this embedding symbol. If I can find isometries U and V, so that when I apply U tensor V on psi, I get my canonical state psi tilde. So I'm thinking of this tilde strategy, kind of some canonical functionality that I want to certify, and of this S as some arbitrary strategy. Okay? So I'm applying this U tensor V onto this strategy state for strategy S, and I'm getting my canonical state tensor some additional state. Okay, and I also want that this U tensor V, if I apply it onto the action of the measurement operators from the strategy S on state psi, then I get the action of the canonical operators from the strategy S tilde on the canonical state, tensor potentially something else. See, I'm not here, I'm acting on this, this auxiliary or ancillary state with identity. All right, so this is what it means for this canonical strategy S tilde to be a local dilation of some other specific strategy S. Okay, and then I'm going to say that this correlation P tilde self-tests or certifies the strategy S tilde, so the state psi tilde, and together with these measurements, if whenever I have any strategy S, which produces the same observations, the same probability distribution, P tilde, then I can locally dilate S to S tilde. Okay, so what this is saying is sort of, if I'm observing P tilde, then essentially the only way I could have done this is by performing this strategy S tilde, okay, up to these local unitaries and attaching of this ancillary state. Okay, I know perhaps this definition is a little bit involved. Let's take a closer look and gain a bit of familiarity with it. So if you look at these conditions 1 and 2, then actually it turns out that this 1 is redundant. Why so? Well, if I fix some x and y, these were my questions, and a and b were my answers. And if I fix x and y and I sum over a and b, remember I told you that these measurement operators, they sum up to identity, then I'm going to get identity here and identity over here. So I'm just going to recover this equation 1 from 2. Okay. The reason why I'm including both of them is that in certain cases, we can only establish maybe this condition 1. And in that case, we are saying that this correlation P that self-tests this specific quantum state. Perhaps we're not self-testing the measurements themselves, okay? But if we have 2, then we would say that we're self-testing both the state and the measurements. Okay. There's also some physical interpretation of what this U tensor V is doing. What it's saying, well, if you have some kind of physical devices that are producing this correlation P tilde, then you could do some local operations on these boxes to recover these canonical functionality S tilde. All right. Okay, but as I told you, we are actually interested in kind of noise-resistant version of self-testing. Okay, so robust self-testing. What we do is we simply insert epsilons everywhere in these definitions. Okay, so given an epsilon, it's kind of your tolerance, we're going to say that S tilde is a local epsilon dilation of S. If those equations on the previous slide hold up to epsilon. Okay, so these are vectors, right? And when I say this is equal up to epsilon, I just mean that the 2 norm of the difference of these 2 vectors is upper bounded by epsilon. All right. Okay, and then we are saying that this correlation P tilde robustly self-tests S tilde if for any desired closeness to the canonical functionality epsilon, we can find a delta so that whenever our observations, right, so we have some strategy S which induces correlation P, so this is our observations, they are delta close to this canonical correlation P tilde, then we can guarantee that we can locally epsilon dilate S to S tilde. Okay, so if you want to know that your devices are the functionality of your devices is epsilon close to the desired one, then you need to have observations that are delta close and this self-testing state. All right, and in most, so the way I've stated it here, it's kind of non-constructive. I'm just saying for any epsilon there exists delta. What we often want is that we have an explicit dependence between the 2 parameters. So we might want that delta is some function of epsilon, and we might want to know For instance, maybe we want that delta is some constant times epsilon square. Now, if you want to actually apply it in a real world scenario, then you often care to find the best constancy possible. Okay, all right, so these were the formal definitions. Now, another question that comes to mind when we think about this verification is sort of how efficiently can we accomplish it, right? So suppose that we want to certify d-dimensional quantum state. How many questions and answers will I need in order to do this, right? If this scaling is sort of very unfavorable, maybe it's exponential or doubly exponential, then it might not be feasible to carry out the certification task for larger system sizes. Okay. And maybe I want to start by telling you sort of what's known, where do we stand? So when it comes to self-testing of measurements, not that much is known. So we know that measurements, we know how to self-test measurements in small dimensions, like think this c to the d being, where d is being equal to 2 or 3. When it comes to states, we have much better understanding. In particular, we know that for any quantum state, so for that is entangled bipartite quantum state, you can design a scheme that will self-test this state. Okay, and this also holds true for robust self-testing. Okay, this scheme capable of self-testing arbitrary quantum states, it will require only 3 measurements, but you will have d outcomes, where d is the local dimension of your state. So some c to the d tensor c to the d. All right, and sort of when we think about efficiency in the quantum world, then we want scaling to be logarithmic in this dimension. That's because of how the dimension scales as we add additional quantum systems. All right, now if you talk about self-testing some particular states, for instance, for these so-called maximally entangled states, there are more efficient schemes that will allow you to self-test with logarithmically many measurements and outcomes. Okay, now about 1 year ago, there was this very surprising result by Hong Hao, who showed that actually with just constant number of questions and answers, you can self-test arbitrarily large states, so states of arbitrarily large dimension, in particular these maximally entangled states again. Now, Fu's scheme is rather complex, so we tried to estimate how many questions and answers does it have, and we counted roughly 100 questions. Okay, and it also doesn't self-test the measurements. So what we were able to do is to use some operator-algebraic techniques to show that the same type of result actually can be accomplished with considerably simpler scheme, and which also self-tests measurements. Okay, so for us, we still self-test these maximally entangled states, but we do it in 2 outcome measurements, and we have only 4 of these measurements, as opposed to 100. However, our scheme also has downsides as compared to this original result by Fu, namely that we don't, our epsilon delta dependence in this robustness result is non-constructive. So all we can show is that for every epsilon, there exists delta, but we don't know what's the relationship between epsilon and delta. And we are currently trying to improve this aspect. And maybe this is a good point to mention that these self-testing techniques, so I explained them to you as being a tool for certifying proper functioning of quantum devices, and this is how they originally emerged. But kind of lately, they've been increasingly used as a proof technique in order to prove some bigger statement in, say, complexity theory. So for instance, this maybe you have heard about this resolution of Conn's embedding problem that was accomplished using quantum complexity theoretic techniques. So self-testing is a crucial ingredient behind that proof. All right, so now I want to move on to the second part of my talk and show you what how do we accomplish this, how do we achieve this theorem? How do we show that arbitrarily large measurements and states can be self-tested using very small number of measurements with just 2 outcomes. Okay. So what we're going to do is we're going to construct an infinite family of correlations P tilde. So this family will be indexed by 2 things. So a natural number n, that's at least 3. And then for every n, there will be some family of x's. And these x's, there will be infinitely many of them for all n that are at least 4. So for n equals 3, there's just finitely many x's, but for all bigger n's, there are infinitely many of them. You can think that there's kind of actually like a table of these correlations, right? I have these n's starting from 3, 4, and so on, and then for every n, I have some allowed values of x, and these are these x's. They are enumerable. You can recursively construct every next x from the previous one. All right. So what are these correlations P tilde? The way we build them is from these projections. So we take n projections that add up to constant times identity. Okay, so this is where these 2 parameters n and x come from. Okay, so now if you just pick some n and x, then you're not guaranteed that this you can indeed find these n projections that satisfy this equation star. Okay, there has to be something special going on. All right, let's just see one example to have a better idea. So one way we could do it is if we take n symmetrically placed unit vectors. So, okay, for instance, for n equals 3, we would take these vectors that are placed like a Mercedes sign, right? And then we consider projections onto these vectors. Okay, but because they are so symmetrically placed, if you add all of these unit vectors up, so you're taking n of these vectors in dimension that's 1 less than the number of your vectors. So if you add these projections, because these vectors are symmetrically placed, what you get is an operator that's proportional to identity, and this proportionality constant is n over n minus 1. Okay, and actually it turns out that so this is kind of one solution, right, to this star equation for this specific value of x being equal to n over n minus 1. But if you ask what other solutions are there to this star equation for this specific value of x, right, x being n over n minus 1, then it turns out that you can get all of them by just considering these specific projections, potentially tensoring with them with identity of some size. Okay, so you would say kind of that this is an irreducible representation. There's only one irreducible representation, and it's this one for this specific value of x. Okay. Now it's not so easy to understand for which values n and x solution to this star equation, but luckily for us, Krugak, Rabanovich, and Samoylenko have done this hard work, and they have classified the situation essentially. Okay, so for every n greater or equal than 3, they find this set gamma sub n of scalars x for which this this equation has a solution, and moreover they study the representation theory of these relations. So how many different solutions are there, right? How many irreps are there? And they identified this subset lambda of n where there's just one irreducible representation. Okay, so for the set of scalars in this lambda n, whenever you have projections that add up to, you have n projections that add up to x times identity, then they take this specific form where these p tilde is your irreducible is your single irreducible representation. Okay, and we are interested in this set lambda n, so we will take values x from this set lambda n. All right, so these were the projections that we're working with. but we need this quantum state and this canonical strategy that we are going to self-test, right? Certify. So how do we build a strategy from these projections? Well, first, so remember quantum. So for every n and x, so n greater or equal to 3 and x in this set lambda n, where your where there's only a single irreducible representation for that star equation on the previous slide, we have one strategy, this S tilde. The strategy, remember, was a triple, so the shared quantum state, measurements for Alice, measurements for Bob. So the shared quantum state for us is this maximally entangled state I mentioned before, and here is the definition of maximally entangled state. Okay, these EKs are the standard basis vectors. Okay, you just take kind of a uniform sum over all of them, and this is a unit vector, right? So this is the shared quantum state. It lives in space C to the D, tensor C to the D. And then for every projection, we build a measurement, a 2-outcome measurement. So we take that projection and we take identity minus that projection. Right? And this, of course, forms a quantum measurement because these are positive operators and they add up to identity. Okay, and for Bob, we again use the same projections, we just take the transpose of them. So what we are self-testing is this maximally entangled state, and these measurements built out of these projections that add up to x times identity. All right, we give a name to the correlation induced by this strategy S tilde, and we call it P tilde NX. And informally speaking, the theorem that we show is as follows. So if you have any quantum strategy S, which produces correlation, these observations that are close to these canonical ones, these P tilde, then the strategy S must be close to this canonical strategy S tilde. Okay, and here's the kind of the formal statement. So for every n greater or equal to 3, for every x in this set lambda n, where this representation was unique, so these P tildes now is this unique irreducible representation. And we say that for every epsilon, we can find a delta such that if we have a strategy S, which induces a correlation P that is close to this canonical correlation, so delta close, and then S tilde must be an epsilon dilation of S. Okay, so epsilon dilation, that meant that I can find these local isometries, this U and V, where the action of operators from this strategy S on the state psi, these U tensor V, it maps it close to my canonical strategy. So the action of canonical operators on the canonical state, tensor some auxiliary state. Okay, so this is the theorem that we show, and let me give you some idea of the technique behind it. All right, so in my opinion, there's one kind of problem with these self-testing statements, and it's that they seem to be often proved using some ad hoc techniques that work maybe for the particular correlation or particular game at hand, but not in general. There's one exception. There's this one proof strategy that proceeds by making kind of connection between representation theory and these self-testing statements. Okay, and the way that this proof strategy goes is as follows. Okay, if you have some kind of setup with underlying group structure, so the first step that you do is you identify this group G. Now the problem is that it's not always the case that you can. It's not always clear how to find this group, and probably it's not even always possible to find this group. But in certain cases, it is possible to identify this group G and show that kind of near optimal strategies correspond to approximate representations of this group G. Okay? And then the last step is to use Gowers-Hatami theorem that says, kind of informally, what it says is that if you have an approximate representation of a group, then you can find an exact representation nearby. Okay, so this is this kind of general proof technique that works if you can identify underlying group structure. Now, in many cases, actually, we don't have this underlying group structure, and what is more natural to talk about is underlying algebra structure. And that's also the case for our correlations P tilde and X. Okay, so we are trying to proceed similarly, but now we have an algebra. So this is, we look at a C-star algebra, the script P and X, that is generated by n projections that add up to X times identity. Okay, now we need to do the second step. So we need to show that near optimal strategies lead to approximate representations of this algebra. And in order for us to get a self-testing statement, it is crucial to pick the right definition of approximate. And I will show you what is the definition of approximate that we need. Okay, and then we need to do something in place of Gowers-Hatami, but let me return to that afterwards. So now I want to show you what notion of approximate representation do we need to use. All right, so we are working with algebras that are specified by some set of generators that satisfy certain relations. Okay, that's where we're at. Okay, so suppose that you have a list of polynomial equations in some non-commutative variables x1 up to xn, and also their adjoints. Okay, so and now I want to talk about approximate representation of approximate representations of these set or family of polynomial relations. Okay, so I will have two things. I will have delta, which characterizes how close to being an exact representation of these polynomial relations do I have, and I will have sigma that will tell me what that will give me the norm that I'm using to measure this closeness. Okay, so I have delta, my closeness parameter, and I have a density matrix sigma. So what is density matrix? It's just a positive semi-definite operator with trace 1. Okay, then we're going to say that the matrices x1 up to xn in some dimension r, they form a delta sigma representation for this list of polynomial equations f. If I have that for all of my polynomial relations fi, this norm is at most delta. Okay, so and it's important that the norm I'm using here, it's not like the spectral norm, like max eigenvalue, or but that we are measuring it on this density matrix sigma. So this is the norm that is relevant in the context of self-testing statements. Okay, so I'm kind of measuring the trace of this operator, but weighted by this operator sigma. Remember, this is a positive semi-definite operator with trace 1. All right, so this is the notion of approximate that we need to use. And with that in hand, it's not so hard to show that near optimal strategies lead to approximate representations of this algebra P and X. Okay, but now we're kind of faced with this hard part of what do we put in place of Gowers-Hatami theorem. And actually, our analog of Gowers-Hatami theorem is precisely where our non-constructive epsilon delta relation comes from in this final robust statement that we obtain. Okay, so I'll show you now Gowers-Hatami theorem, and then show you the theorem that we were able to prove for this particular algebra P and X. Okay, so here's the statement of Gowers-Hatami theorem. Maybe it's good. This is a good point to mention that Gowers-Hatami didn't at first prove this theorem for this state-dependent norm. So where I have this arbitrary positive semi-definite trace 1 operator sigma here, and it was extended by Thomas Wittig for arbitrary sigma here. Okay, so what we have here is a finite group G. Then I have a dimension R, and kind closeness parameter epsilon, and again, my density matrix sigma. Right, and then I have an approximate representation tau prime. So again, I'm measuring, it's an epsilon representation when I measure it on this state sigma with this state dependent norm. Okay, and it says that whenever I have this approximate representation tau prime, then I can find an isometry V and now an exact representation of my group tau in some dimension capital D, so that for every group element I have this inequality. Okay, so it's saying that this tau prime is kind of close to a corner of exact representation tau. And what's important here is that this upper bound on this norm, it doesn't depend on the dimension that my representation tau prime was in. It doesn't depend on R. It only depends on the size of the group and the quality of my representation that I started with. Okay, and it also has a good dependence, right? It's just square root. It's not it's not something that scales exponentially. All right, so here's what we were able to show for this algebra P and X. So so again, we want to show it for every n greater or equal to 3, and these x's that lie in the set where we have a unique irreducible representation. We show that for every epsilon there exists delta and a positive integer m, such that if we have operators E1 up to En and some density matrix sigma that satisfy the following two conditions. So the first condition says that these operators E1 up to En, they form a delta sigma representation of these relations defining our algebra. And the second requirement is it's essentially saying that this state sigma, that it is approximately tracial on the words or monomials that have degree at most m in these variables E1 up to En. So if these two things are satisfied, so then we can find this isometry analogous to the case of the one in Gowers-Hatami. Of course, in our case, we have this non-constructive epsilon delta relationship that I already mentioned before. Right? For every epsilon, we can guarantee that there exists this delta, but we would like it to be fully explicit and preferably with some nice scaling. All right, so this is what we were able to do in this case. And I would be very curious to know, like, under what conditions can we obtain, for what algebras? Maybe I promised to you that your algebra has a unique irreducible representation. Under what conditions can I guarantee that an analog of this Gowers-Hatami theorem exists? All right, so let me just recap what I told you, what we've seen through this almost an hour now. Okay, so we were talking about self-testing of quantum devices, so verification with minimal assumptions. And the way that we built our verification scheme was we started with some projections, and projections that add up to X times identity. And using these projections, we constructed a quantum strategy, right? We measured maximally entangled state using measurements that are built out of these projections. So we had n measurements for Alice and n measurements for Bob. And this gave rise to this joint conditional probability distribution or correlation P tilde nx. Okay, and informally what we showed is that if you observe a correlation probability distribution that is close to this P tilde, then you know that your strategy must be close to this canonical strategy. So this canonical strategy, it measures maximally entangled state using these measurements built out of this single irreducible representation of this algebra Pnx. Okay, so but now let's specialize this result to n equals 4. Okay, so for n equals 4, the set lambda n, so lambda 4, is given by these fractions. Okay, and in particular, the dimension of the corresponding strategies is the denominator of this fraction. So so this is going to be strategy with local dimension 2k plus 1, and for every natural k. All right, so then these correlations, they will just have 4 questions because the number of questions corresponds to the number of these projections, this n, and they will have only 2 answers. The interesting thing that it's the size is constant. However, the dimension of these irreducible representations, right, it grows. So the dimension of the strategies that we are certifying, it grows arbitrarily large, right? Grows as this 2k plus 1. Okay, and this shows that these constant size correlations are capable of certifying both arbitrarily large states as well as measurements. Okay, that's all I wanted to tell you today. Thank you very much for your attention, and I'll be happy to answer any questions.
Thank you very much. Let's thank the speaker. Okay, are there any questions?
So let me understand a little bit better what you're doing. So you motivated your talk by saying you have, for example, a very large quantum system, and you want to certify that they're doing what they're supposed to do. Your projectors, on the other hand, that you're choosing are only, or like 3 or 4, something like that. So if I understand your proposal correctly, this projectors you're doing is a huge collective measurement on your quantum system with only 3 or 4 or 5 projectors as one of the questions you're posing. Do I understand that correctly?
Yes. So what this result says, right? It's not saying, it's not telling you how to self-test an arbitrary state in arbitrarily large dimension. What we are showing is that there is a family of arbitrarily high dimensional strategies that you can self-test from sort of, so to speak, a setup with finitely many measurement settings, and not just finitely many, but like fixed number, right? So 4 questions and 2 answers.
And so these are not full right projectors, right? This is measuring some huge subset of the entire Hilbert space.
So they will be, their rank will grow. Is that the?
Yeah, I guess the point is if you have full rank projectors that span the space, your chi would be 1, right? So the fact that chi is less than 1 means you're measuring in some subspace.
So sorry, chi?
Or x, your first equation. The sum of p's is chi times I.
Yeah, so to get this constant size arbitrary large dimension result, we're taking n equals 4, right? And you're right, they're filling up the whole space. So and their dimension grows, right? As x. So you can think that these x's are enumerated. There's some x1, x2, x3, x4, and so on up to infinity, right? They are these fractions, right? They're indexed by k, right? Natural numbers. And the rank of these projections will, of course, have to grow as this k grows, right?
So k is a sequence of possible systems?
So it's a sequence of strategies.
Sequence of strategies.
Right, so we are self-testing a sequence of states. Actually, the states are all of the same type. They are these maximally entangled states, but their dimension grows. Right, you take this uniform linear combination of EI tensor EI, where EI is the ith standard basis vector. That those are the states you're certifying.
Thanks.
Thank you. Any other questions?
Hello?
No? Okay, if there are no more questions, let's thank the speaker again.